This is lesson 58, BHDL example 35. And in this example, we'll design an 8-bit divider using a BHDL procedure. You remember from the last lesson that this algorithm will divide an 8-bit numerator by a 4-bit divisor to get a 4-bit quotient and a 4-bit remainder. But to divide an 8-bit numerator by a 4-bit divisor and to get an 8-bit quotient and a 4-bit remainder, you remember we needed to call this 4-bit divider twice. So this is a good example of where we might want to use a procedure. You remember we used a procedure back in lesson 36 on example 20 where we made a 4-bit comparator. So let's see how to do it for this division. We're going to take an 8-bit numerator, 7 down to 0, a 4-bit denominator, 3 down to 0, but we want the quotient to be 7 down to 0. That is an 8-bit quotient and a 4-bit remainder. So this is the entity for dividing 8 bits by 4 bits to get an 8-bit quotient and a 4-bit remainder. So here's how we're going to do it. We'll first design this 4-bit divisor, we'll call it div4, using a procedure. Now remember in the procedure we list the inputs and outputs much like you would in the entity. So here we'll call numer the 8-bit numerator and we'll call denom the 4-bit denominator. Now we'll use quotient and remainder here as well for quotient and remainder, but this quotient is only 4 bits, 3 down to 0, and this remainder is 4 bits, 3 down to 0. But these are different quotients and remainders than in our entity for our 8-bit divider. So we have a variable d and n1. These are 5 bits, and n2 is 4 bits. So here's our little algorithm that we want to implement. So we need to store the numerator in the concatenation of n1 and nd. So the numerator, 3 down to 0, goes into n2, and the numerator 7 down to 4 with a leading 0 goes into n1. The denominator with a leading 0 goes into d. Store the denominator in d. Then we want to repeat 4 times, so we'll go through this for loop, 0 to 3. And we need to shift n1, n2 left 1 bit. So n2, let's shift this one first. n2 gets n2, 2 down to 0 with a leading 0. And then n1 is going to get n1, 3 down to 0 with the uppermost bit of n2 shifted in. So this will have the effect of shifting n1, n2 left 1 bit. Then we have to see if n1 is greater than or equal to d. Well, if n1 is greater than or equal to d, then n1 gets n1 minus d, and n2 0 gets 1. Okay? And we do this 4 times. So that's the for loop. And then when we're done, the quotient is just in n2 and the remainder is in n1 and 3 down to 0. So this procedure implements our 4-bit div4. So to get our 8-bit one, we need to just call this twice according to this diagram we have here. So the process will be numerator and denominator in the sensitivity list. We'll have variables for remainder high, remainder low, quotient high, quotient low. Those will all be 4 bits. And then we just call div4 twice. The first div4 will implement this one, where we want 0 numerator high coming in for the numerator. So we have 0, 0, 0, 0 concatenated with numerator 7 down to 4. That will be this one. Denominator will be the denominator coming in here. And the outputs will be quotient high and remainder high. That's quotient high and remainder high here. So that's what this first div4 will produce. The second div 4 is going to get this one. Well, it's going to use remainder high from here. Right? So this remainder high gets concatenated with the numerator low, which is numerator 3 down to 0. The same denominator comes in, and the output will be quotient low and remainder low. Then the output 8-bit quotient, 7 down to 0, will be made up of quotient 7 down to 4 is quotient high, quotient 3 down to 0 is quotient low, and then the output remainder is just remainder low. So this is how we can implement an 8-bit division where we divide 8-bit numerator by a 4-bit denominator to get an 8-bit quotient and a 4-bit remainder. And we can test it with a simulation. Here we take a variety of numerators using a binary counter. We'll divide by 5, and here is the 8-bit quotient, and here is the 4-bit remainder. And you can check these. 43 hex divided by 5 hex is 0D with remainder 2. Here's one you can do in your head. 64 hex is 100 divided by 5. The answer should be 20. And here's quotient 1,4 is 20 with remainder 0. So you see it works. And these other ones you can verify. And we also show all the intermediate quotient highs and quotient lows. And so you can go through those and verify that in fact we now have a divider which will divide an 8-bit numerator by a 4-bit denominator to give an 8-bit quotient and a 4-bit remainder.